Hello, I'm Sergei Müttü. I'm backend developer in Taxify, and today I'm gonna be talking about dynamic pricing. So initial plan was that it was just me talking, but at the last moment we decided that Andre, our data science team lead, will join, and he's gonna talk about data science a bit, like details. I will start talking, and questions and discuss. If you have any questions, please hold them. We will have them at the end of the talk. All right. So aim of current presentation is to give you some insight how we're actually working in Taxify, what we actually do and how we do here. So dynamic pricing is just one of the problems we're actually trying to solve, and why we actually selected it for current presentation, because it's like hard and interesting at the same time. Hope if you like it. What is dynamic pricing and why it's actually used? A bit of theory. One of the basic law of economics, supply-demand law, states that any product, the price of any product determined by balance between production, basically supply, and desires of people who are actually willing to buy by demand. And at this particular diagram, for example, we have like quantity below and price here. Demand curve is increasing, demand is increasing, and to actually balance the system, price has to also go higher according to the supply curve. So this is like theory. In reality, the price adjustment doesn't happen automatically. So many companies, like many industries, trying to achieve that, introducing some sort of price automation, like airline companies doing that for ticket prices, hotels do that, internet shops like Amazon is the like first example which comes to mind. And of course, ride-sharing companies as Uber, Lyft, and Taxify are also trying to do that. So here in Taxify, what dynamic pricing means for us exactly. So dynamic pricing for us is the black box, a system which takes some parameters in. Riders, drivers, traffic, maybe weather, something else. Like some city particular properties and so on, and as a result produces the price. And it does it like, oops, sorry. And it does it in real time, very fast, and for many geographical locations. So in particular cities, there can be like hundreds or millions, from 100 to millions different geographical locations where we're actually calculating dynamic price. And this is just a part of the task. It would be actually nice not just calculate price in real time. It's also nice to predict it in future. So like what price is gonna be like next day, next week, maybe even further. Challenges. What are the challenges solving the dynamic pricing? There are actually two parts. One is kind of technical, scalability, another one algorithmic. Technical. Why technical? Why it's complex. So taking the previous definition from previous slide that dynamic pricing has to be calculated in particular geographical location in real time. Let's take, I don't know, some city example. Here on the screenshot, I have heat map of Paris. This is some day situation there. And Paris area is around 100 square kilometers. And if we split this area into like small boxes, let's say like 100 by 100 meters, you will get like million boxes. And if you calculate price for each of these boxes in real time, then task becomes like really complicated. And if we presume that we are actually operating in multiple cities, like tens of cities, and some cities are like much larger than Paris, for example. So I don't know, it was like actually surprise for me that according to Wikipedia, Paris area is less than Tallinn. So Tallinn is 150 kilometers square. But there can be like even bigger cities. For example, in Africa, we operate in Johannesburg, which is like 16 times largest area-wise than Paris, for example. So calculating the dynamic prices in all these cities in parallel, in real time, becomes like computationally expensive task. Algorithmic part. The difficulty there is having all these parameters like drivers, riders, traffic, situation in different locations, how to actually figure out price based on that, how to find that optimal price which is good for drivers and for riders at the same time. So this is the task of kind of algorithmic part. And of course prediction of the price is also important. I will continue with kind of technical part, but before talking about like technical aspects of dynamic pricing, I will briefly run through Taxify backend, how we work, how we operate. So basically, dynamic pricing is mostly operating in backend. Of course, some information produced by dynamic pricing is exposed to mobile application and so on, some visualization, but main functionality is in backend. And Taxify backend is implemented as microservices architecture based on Node.js. We have Node.js, JavaScript, REST services. Initially, everything was JavaScript. Now we're gradually migrating to TypeScript. Everything is running in Amazon cloud. We don't have anything hosted locally. Everything is in elastic computing. We use Docker for replicating different environments, for testing, for integration test, for local testing, and so on. Databases. The main database we use, the cornerstone of Taxify, is MySQL, MariaDB. Basically, mostly all the data is stored there in a relational database.
So it is MySQL, yes?
MySQL, yeah.
And what is MariaDB?
MariaDB is engine for MySQL.
If you have any questions, then there
Yeah.
will be a question answer.
At the end, we will just have questions and discussion. For fast data, for caching, we use Redis, and for long-term storage, we use Redshift in Amazon, where we store our statistics, something which we don't write that often, but read a lot. And finally, file storage is S3, Amazon S3. So most our infrastructure stays on Amazon. All right, back to dynamic pricing. So dynamic pricing can be viewed as sort of technical platform running a set of algorithms. So like kind of algorithm carriers. There can be like one algorithm running everywhere in all the city, or there can be like several of them running in parallel, theoretically. And dynamic pricing platform provides the data, collects the data from different pieces from other pieces of the system, of Taxify system, delivers to particular algorithm, then collects the data, results, and again returns it back to different parts of the system, like showing it, for example, on some rider application or driver application. Important characteristic of dynamic pricing is scalability. So as Taxify expands, as it moves to new city, implementation of dynamic pricing should like scale along the expansion. So presuming we implemented something and it works fine, it shouldn't be that way that we kind of go to a new city and we have to implement everything from the scratch. So it should basically scale along. In worst case, we just like add more machine and it still works And it also should handle the load. It should handle spikes, which we have like at certain days, at certain time of the day. So we don't have the even load. For example, New York Eve is like one of the critical times where we have like much more load, much more rides, much more riders participating in the system. So everything gets more load. Data storage in dynamic pricing. So when we are talking about results of dynamic pricing, the price, it's actually very transient. So if you calculate the price in the system, you should return it back to drivers, you should return back information to riders, and in 5 minutes, like in a couple of minutes, this information becomes obsolete. So it doesn't make sense to store it to hard drive, for example. So most of the data in dynamic pricing is actually running in memory. From other side, we need a lot of data stored in long-term storage to analyze it later. So kind of we're introducing new algorithm. We want to store all the data possible, like with which algorithm was working. Input data, results, and so on. So we store it in Redshift, in files, and then we analyze it. Data science team works with these files and so on and so on. Geodata, maps. So dynamic pricing is basically built around geodata. It's actually, Taxify in general is kind of built around like position, roads, but dynamic pricing is basically 90% geodata. How we store this data, how we efficiently access this data is very important. So which algorithms we are using to actually access the data is critical. Visualization. So visualization is an important part in like 2 cases. Like monitoring, seeing what's happening in cities, how situation is kind of develops is very important. It should be real time so we can react very fast. And we also should provide some feedback to our customer, like some driver view showing situation in the city, showing like hotspots in the city. And the last, but I think not quite important property of dynamic pricing is being optional. If dynamic pricing crashes, if it goes down, it shouldn't pull everything around with it. So it should just like collapse inside, and other parts of the system or other part of the of Taxify still working. You're losing this dynamic pricing, everything goes to kind of basic fee, but at least it still works. Moving forward to algorithmic part. So how do you actually design the algorithm for dynamic pricing? Why is it like that difficult? So how you start doing that? So before starting implementation of dynamic pricing, from what you begin? Either you implement technical part first, or you implement algorithmic part first. So how we approach it, we first kind of invented very naive implementation of algorithm, very simple. Using drivers, using riders, it's just like divide second one by first one and you get some number. This is something like multiplier. And then moving from there, we kind of in stages improving it and improving. Currently we are at the iteration when we clearly understand that like creating algorithm manually doesn't make any sense. So we're understanding that like future is like machine learning, that machine learning algorithms actually figuring out the perfect dynamic price for us. And this is where kind of data science team comes in. Andre will talk about data science team with details. I want to emphasize I want to kind of speak about how we actually interact with the data science team. What is the complexity of process between development and data science team. How we prepare data. So the main thing data science team needs is the data. Data has to be retrieved from different pieces of system. It should be prepared, kind of cleaned a bit. So part of this job kind of on developer side. So data science team says that we're missing that data. Basically, I have to implement the way to store it, to provide it to them. As long as data science team got the data, doing the magic, producing some result, some model. This model has to be integrated back into the components. How to plug it into the code, how to scale it along with the system so it doesn't slow down all other pieces. It's also important. Currently, all the data science main language in data science is like Python. Along with R, I think we are using Python, and even me as a developer, like I'm not doing this data science part that much, but working with Python is also like very convenient. Like preparing the data for them, evaluating the data, debugging errors helps if we are using like similar tools data science team actually does. So we are using Jupyter notebooks, basically running Python on web. This brings in convenience in solving like that, in preparing the data. And from my side, this is it. Andrei will continue and we'll talk about data science. Thank you.
Hello, I'm Andrei, and I will give you a brief overview of data science, how we work with Sergei, other engineers in the company, so that you have a better sense for what it means to create models for dynamic pricing, or models at large. So just a recap for everyone. So this is a simplified process of data science and what it means. You have to first have data. So you collect the data, you have to process it into a format that your models can use. Usually it's in a different format like protobuf, you need to convert it. And then you have to clean the data from errors so that the models produce accurate and good predictions. To find the right patterns, there is an activity called exploratory data analysis where you look for relationships between variables, and then once you find valuable patterns, you create machine learning algorithms for this that you productize. And all this happens while we communicate with Sergei, engineers, business, so that we can make the right decisions. And now going a bit more into detail, so how do we work? So first about the pre-processing and cleaning of the data. So you have data sets. We have tens of terabytes of data in Redshift, S3, Elasticsearch. At peak load, we have about 860 million requests per day. Then billions of routes. All this data has good and valuable data sets, but also things that you need to clean. So here is an example of a subset of small data set where you transform the features for your models into a meaningful format. So you can see the steps in data cleaning. And for every model, every data set you work with, you have to do this. So you have to impute the missing values. Sometimes you have to do data augmentation, creating new data from the existing data. If the data is very highly dimensional, you reduce the dimensionality. Basically, remove any inconsistencies and errors in it so you can use it. one thing we do a lot at Taxify is automatic machine learning. So we try to prototype as many models and methods in parallel to find good performing methods. And this automatic machine learning approach allows us to try out many different predictive methods. It also does automatically cross-validation for you. You can select the best metrics for a particular task. And here you see just a list of different models and ensembles performing against a very specific task. So these are trained in parallel on the infrastructure. So far, the benefit of this is that we can do very fast pilots. So we find something interesting, we can go quicker to live. And we have created more than 300 models per week using this approach. Then once you have a good approach, good method, then what you do is you write code, of course. And this is done together with engineers, because things we have to optimize for is low latency for real-time events, and also thousands of predictions for batch data. And here you can see just some examples. So we work for one model, we work with light GBM, gradient boosted trees, and its benefit from compared to XGBoost, for example, which you might know, is that it has a leaf-wise growth architecture, which gives you faster convergence to a good result, and also you have to limit the overfitting with max depth of the trees. And you iterate with these models in Jupyter Notebook, as Sergei showed. And then what we do, we compare different models to each other, compare it also to the baseline we have in live. And here you can see, for example, for estimated time of arrival, 3 different models, what is the error they produce compared to the actual duration it took for the driver to get to the rider. So we look a lot at distributions, many different metrics, and once you have a good model that you deploy to live, so right now we generate JavaScript for our NPM package manager from the runtime model. So what you do, then you continuously improve these models, and this happens interactively with the engineers. Here you can see the estimated time of arrival I showed you before, how it relates to the surge multiplier that Sergei talked about. So what you can see from these distribution graphs is that the failing rides, when someone wanted to take a ride but couldn't, are different compared to the good rides where someone got the taxi, completed the ride. You can see that the distribution of the rides is much more different for the failing rides. And this information then we can put back into our algorithm development and decide which algorithm to release in which city. So this is a very quick overview of data science part, what we do at Taxify. And now it's time for questions. And also before giving the floor to you, so we are also organizing events. Next one coming up on 8th of March. It's a machine intelligence conference for developers, where we have invited many different people across the globe, from US and Europe. So, floor back to you.
Questions?
Right now we have around like 10 or even more minutes for questions, so in this sense we're really safe.
So, what tools or framework do you use for machine learning? And that's the first question. The second one is, you mentioned that you are using ML for like price prediction and ETA. Any other applications?
Yes. So machine learning is interesting in sense and data science that it can be applied in many places where you have data, and Taxify has a lot of data. So finding the best routes, time of arrival, marketing campaigns, fraud detection, outlier detection, basically the backlog is really long. Many places where we can apply data science. Here we talked about dynamic pricing, ETA. These are the core related to this. So the tools we use are what you would expect us to use. So in Python you have scikit-learn, pandas, numpy, scipy, all the usual stack. Jupyter is used a lot. For visualization we use a lot. For decision making we use Looker. And we know that for us neural networks make sense. Right now what I talked about was just decision trees. So for this we use LightGBM. So that's the main library for live at the moment.
Yeah. What was the name?
LightGBM.
Does the model or the phone influence on the price? For example, if in some area there are lots of people with iPhone X, will you raise the price for them?
No, not now.
Not yet. Okay.
Not yet.
Because statistics may show that you have to raise it.
Yeah, this can be like phone model is one of the factors which can be considered, like while calculating the price.
There was a question.
Yeah, a user perspective question. So I use Taxify number a lot, and I was speaking once with a driver saying like, so my radius, the cars are shown to me, are actually much less than the driver can see in the radius of the car to be pulled. Is it a bug or a feature within the app? Yeah, follow what's up. Yeah, so when you're pulling the cars, is it actually you're sorting it like more just by the radius, like actual direction the car goes, or because what the driver told me, because when he logs in the app, say like, oh, I can wait for a call, like say an hour or 2 hours, but when the user logs in, it's like he just doesn't see the cars around him.
Well,
Maybe have bad rating.
it depends on the situation in the city. There can be cases when they're like high demand or like a low demand. So like from driver perspective, it's like always low demand, right? From the rider perspective, the demand is also always too much, so you don't get any cars. So it's hard to say that. Like I think this is like working as expected. No, so
it's a feature then, okay.
It's feature, yeah, I guess.
So, question about you.
Do you have the instances where drivers try to game the system, automatical system, and create search prices so they will benefit from it?
This is actually one of the interesting aspects of dynamic pricing. This is actually the case. Driver trying to simulate the demand, basically opening application, rider's application, like agreeing between each other in Facebook and trying to basically search pricing. Yeah, this is definitely the case. There are also like some bots trying to scan, in some cases just trying to gather information about, for example, our dynamic pricing. In some cases trying to affect our decision as well. So this is the factor which affects us.
Excuse me, there was audio.
Just to better understand the business impact of machine learning, can you bring out maybe some kind of, let's say, a multiplier benefit to what have you gained with machine learning instead of like using a simple algorithm which you described in the beginning of the talk? How much better is, let's say, this rejection rate because the client can't do it enough, or what's the added benefit in business terms?
So in business terms, machine learning produces incremental value. And the baselines you create, simple ones, are quite good usually. And there is, business-wise, there is diminishing returns. You add more complexity, you get less result. But for example, with decision trees, compared to the simple approach, we've been able to beat some of the baseline models quite good. And we know that the next step, like neural networks or more complexity model, will produce a smaller step. So one of the things we had to do with a small team there are a couple of things. So on one hand, we try to automate as much as possible in machine learning to keep the team efficient. And the second piece is we look at where we can create the biggest jump in performance. So for dynamic pricing and ETA, so with ETA we found better models. So and we know that for users ETA is really important. So it has to be accurate. So we continue investing in this. But at some point we will see that the value grows smaller, then we decide not to use it. Other example like fraud detection. You cut the fraud by a couple of percentage points, it translates into direct money. So it depends on the business case, on the use case, what metric do you use.
Thank you for the presentation. So my question is about as I'm far from machine learning. For example, if in software there is unpredictable behavior, how to separate that it's software bug and not unpredictable behavior of machine learning results and otherwise?
So for example, for dynamic pricing, so what we did, we added some constraints in defining the target. We said that the model cannot produce extreme multipliers. So you have to add some rules around the models to make sure that they operate within constraints. So that's one thing you do.
In some sense, in the end, this like data science model, it's like piece of code. So if it starts giving out some like unexpected results, you just like debug it as well.
But if result is not constantly repeated, so if predictable behavior happens sometimes.
Well, this is like complex case. This is, I think, something similar to multi-threading. So if you have like when you have non-deterministic errors happening sometimes, it's like very similar.
So one thing we aim for is instrumentation of what we do. So if, as I mentioned, elastic, so we get requests, we know the context in which an algorithm was executed. So storing this data is an aim for us. So we want to store the data and the context around the execution runtime so that we can mine for the patterns in the data if necessary. A lot of the exploratory data analysis is actually about finding out about the outliers, the relationships between variables. So it relates to the debugging, to understanding the system better. And Taxify is interesting in the sense that there is this physical part of like physical city, real cars, and then there is business part. So these two together mean that we need to collect a lot of data in decision making. Yeah, lots to explore.
Yeah, I have a question. So it was quite a while ago when Taxify was presented on DEVCLUB last time, like around 3 years ago. And then was a question, like what if ordinary person pretends to be a taxi driver and he just like reduces himself as a taxi driver and starts serving and just not really licensed stuff, like doesn't seem to be. So now we have machine learning. Can you predict person that he's actually not a taxi driver? And just like he's like really suspicious type, and maybe we have to exclude him from the driver list?
Like a free card.
Yeah, user profiling, so you can do a lot of user profiling.
But do you do it for drivers from now? Just in order to understand that maybe they are not really good ones.
We started building our data science team in November. A lot of things we can do.
Yeah, but do you do it?
Right now, we focus on areas you saw. Some other areas, not driver profiling. We work with fraud, of course.
Mm-hmm.
So fraud is an important case. People work with data a lot there, also with models. So and this goes into this category.
There is one area is like predicting driver movements and how to drive the car. So this is something we will actually pick up. So to see how are the drivers driving around. If some drivers are driving recklessly, we can have them training on how to drive safe. So this is like just one of the examples that we can actually do.
My question was on here.
So you were talking about your ETA model. So have you done comparisons like is more accurate or less accurate when like comparing to Google Maps or Waze? Or do you have any data on that?
So I would not comment the specifics, but what you saw were the real models, the real baseline against each other, different distributions. Results look really good.
I can add one example. So with Google Maps or map-based ETA, so you look at the map and track, and you assume that the person drives legally, right? But we saw that actually the ETA was always less than actually possible. And analyzing those cases, we realized that they do illegal U-turns or illegal turns. And if 95% of drivers do this, it means the ETA is actually lower for this case. And machine learning picks this up. And if there is a new road or they know the shortcuts, they are really smart. So this is what machine learning picks up. And also there is this difference in behavior. So if the drivers are driving a lot, they are a bit faster than the average person. And this means that this is also something which we can take into account and have more precise ETAs. And this is a real case, and that's why it's more accurate.
What's the benefit of using this dynamic pricing compared to static price? Like in normal taxis, they have static price per kilometer.
Well, it allows, first of all, I think the intent is to balance the system. So like when demand is growing and price is growing along with automatically, then if you take like some geolocation, a lot of people trying to get a car and there's not enough supply, dynamic pricing react, we show it on the map and drivers actually see the situation and they're trying to move there. And in that sense, we kind of restore the balance. Also, riders, if they see like high price, some of them actually like abandon their attempts and going like by bus or something like that. So in that sense, we sort of balance the system, balance the situation in the city, and at least theoretically, like kind of improving the kind of impact on the users, basically, something like that.
Thank you.
After working on this machine learning GPS, I have plans to work on self-driving cars.
So self-driving is something that's already happening. L5 cars in Singapore, trialed in US. So we have to be aware of these cars. We are not robots company. We are optimizing the city urban transportation. So we have a fleet of drivers, we have a fleet of cars, and we have to see that the mix of those works well right now, also in the future.
What are possible fraud cases you have to fight with? Who frauds, drivers or people, clients?
People are trying to be smart, like riders and drivers are both like trying to.
Can you give example of the fraud case? I cannot imagine. Like I don't understand.
So the easiest explanation is that anywhere where you have a credit card, you have fraud, and that's you can think from there. So.
But do some drivers do GPS spoofing, for example?
Well, drivers, like one of the simple ones, drivers just like simulating the rides, basically. The two guys agree between each other and they just like log the ride, but like, trying to log the ride and get some money for us.
Yeah, but somebody got to pay for this, right? For example, if somebody simulates the ride, you charge them for real. And then, like, driver gets less commission than you charge.
Money laundering.
We have this
Because
bonus.
if money was stolen, credit card maybe.
We have the bonus system as well, so this is also taken into account.
Any more questions? Yes.
A question regarding the company's culture. Like in many companies, the number one value is customer first, and then there's team and etc. etc. But in your case, the customer is both the driver and the end customer who wants to drive, right, on the taxi. Who do you kind of give the first value? But I mean, this is an important question, right? Because I would say the end customer who drives, but what do you say about that? Like, how do you prioritize?
Ryan?
So yeah, so actual answer is equal, kind of. We have to prioritize both. So drivers are the ones who are offering the service. If there are no drivers, we can't offer this service. So we have to equally balance this, and then we are giving them jobs. So it's important that they can rely on us, and same way our clients need to rely on us to get the ride when they need this. So it's equally important. I don't say we prefer any. But yeah, both of them are most important thing for us. So that's for sure.
Yes, and this is the last one.
Just general question. Maybe could you underline main differences between Taxify and Uber? Your advantages.
So we offer better earnings for the drivers. Our commission is smaller. This means also a better ride price for the customer. And we, as a company, it has been able to be really efficient in use of investors' money and own money. So business-wise, it's a very sound company. That's one of the difference.
And maybe to that, so this is also one of our challenges. So if we talked about data science team, which we recently started, so we have to do with this small team much more than others have done. And that's why we are using automatic machine learning and many others. So basically we have to choose as smart ways as possible to do more value. So this is a big challenge for us. We are always looking how to do this, how to build less on our own, how to use services, how to be more effective. And this is across engineering team and across business everywhere.
So thank you guys. It was really nice.
Thank you.